Hi all. In this video we will see that BLDC motor speed and torque characteristic, and we'll also able to analyze that how BLDC motor can cope up with the requirement of the high acceleration for the short period of time. And also, as we know that the BLDC motor is electronically commutated motor, so we'll see that how the switching of the BLDC motor happens and then how it produces the required torque along with the timing diagram. So let's start. So here we have the typical curve of BLDC motor with respect to the speed on the x-axis, and we have the torque on the vertical axis or the y-axis. Over here we can see that the BLDC motor works in two torque zone. One is the continuous torque zone, which is the one denoted as 1, and the other one is the intermittent torque zone, which is shown over here as number 2. So BLDC motor works mostly on in the continuous torque zone. Here we can see that with respect to the speed, here as we are increasing the speed from left to right, then the motor torque remains constant up to this point. So this point is related with the rated speed. So we can see that up to the rated speed, BLDC motor produces the constant torque. So which is very good advantage of the BLDC motor, as we increases the speed of the motor, the torque does not get distorted, or it does not get reduces or increases, is remain constant over here. So this is the one thing. And from here we can also see that BLDC motor is capable to produce some amount of torque which is more than the rated torque and less than the peak torque load. So this is the torque region which is above the rated torque of the BLDC motor. So in this zone, motor can run for very short period of time. So it is something like this. Let's say that BLDC motor is just starting from here. So the speed is just picking it up. At this moment, the torque produced by the motor can reach to up to, let's say, the maximum, which is given as or shown as the TP, the peak torque. However, as we increase the speed, or as the BLDC motor picks up the speed, the torque, which is the peak torque, amount of the peak torque generated by BLDC motor gets reduces, and up to the coming up to the rated speed, the torque which can be produced by the BLDC motor is up to the only the rated torque over here. So this is the reason where motor can only work for the short period of time. Now let's understand this with the one scenario. Let's say that my BLDC motor is, as of now, is operating at this speed, and which is denoted as A point, let's say over here. And at this point, let's say the motor is producing the rated torque, because up to the rated speed motor can produce the, or motor remains in the region of the continuous torque zone or the rated torque. So let's say that my motor is producing this much torque over here, which is shown as V over here, and suddenly motor requires to produce more torque due to some load requirement. So at this point, motor can reach to the maximum torque of this much value, which is of course lesser than the maximum peak torque which can be produced by the BLDC motor. So the C point shows that the motor can produce this much amount of torque in this region. However, in this region, up to this point, the BLDC motor can remain only for the short period of time. As the BLDC motor is continuously running and we have increased the torque, and the acceleration has also been increased, so definitely the speed will increase. The speed, as we are increasing a speed and moving away from point A, now let's say that BLDC motor has reached to the point D. Now this is, let's say, D, and at this moment the torque which is produced by the BLDC motor, which is maximum, will remain only, let's say it is shown by this point E. However, due to the heating problem, the motor can only remain in this intermittent torque region for the very short period of time. So in a way, BLDC motor is capable to give you the sudden acceleration if it is required, as we need some in EV applications sometime. So it is capable to give you the sudden acceleration and the increased torque, but only for the short period of time. And then again, the BLDC motor will come up to this continuous torque region, and it will able to provide you the continuous torque up to the rated speed. However, as we increase the speed of the BLDC motor above the rated speed, and we can go up to the, let's say, the maximum speed range of the BLDC motor, then the torque is inversely proportional to the increase in speed beyond the rated speed, and then the torque of the BLDC motor also get reduces. So this is the curve, or this is the slope by which the torque of the BLDC motor reduces after the rated speed of my motor. And this is comparatively, it has been shown over here that BLDC motor curve has a flat. It is enable operation at all speed with the rated load. Comparatively with the DC motor, the torque is moderately flat at higher speed, but as the brush friction increases, it reduces the useful torque. And this is specifically, we can talk about the the DC shunt motor here. If you're talking about compared to the induction motor, we know that the torque speed curve of the induction motor is non-linear, and it has an operating region, stable operating region. Beyond the pull-out torque, the motor can come to the halt position. So compared to these two motors, DC motor and the induction motor, the BLDC motor is having the very flat and linear kind of a torque speed characteristic, and the torque speed curve over here. Now let's understand the switching operation of BLDC motor. As we know that the BLDC motor is electronically commutated, and we embed the whole sensor in the stator to on the non-driving end of the motor. So to understand this, for a BLDC motor, we can have single winding energized, and we can also have the three winding BLDC motor, which is generalizedly known as the three phase and the single phase BLDC motor. However, we always keep in the mind that BLDC motor is not an AC motor, it is a DC motor. It runs on the DC. The only thing which abbreviated as the single phase and three phase is related to the windings. If we are having the three windings over the stator, which is placed 120-degree apart mechanically, then it is abbreviated as, or it is known as the three-phase BLDC motor. And if we have only single phase winding, then it can be called as the single phase BLDC motor. So to understand the switching, as of now, we are taking the case of the single winding over here, and we have one Hall sensors which is shown over here with that dot A. And as we see that the switching is being performed with the help of the MOSFET, so we are having the 4 MOSFET or H-type bridge over here. So 4 MOSFET is being deployed to energize the winding over the stator, and the rotor is made of the, let's say that this is of the permanent magnet type rotor over here, and it is having the poles something like NS and S. So we are having the 2-pole pace over on the rotor, and the output of the Hall sensor will be high if it is under the influence of the N pole of my rotor over here, and it will be low if it is under the influence of the south pole. So to understand the switching and how does my switch 1 to 4 operates over here, let's take the rotor position, which is currently situated at this, and at this position we can see that the Hall sensor is under the influence of the N pole over the rotor, and we are giving the modulated pulse to the switch number 1. So the circuit will get completed either switch 1 motor to switch 4, or it will get completed through the switch 3 and then going from the motor. So we can see that the current direction will get changed over here. In this, the current direction was from left to right, and when the switch 3 and 2 works, then the current direction will be from right to left, something like this. So in the first case, we can see that the Hall sensor is under the influence of N pole, and the rotor is running into anti-clockwise direction. So the rotor running direction is the anti-clockwise direction, And from when the Hall sensor output is high, switch 1 and switch 4 will get closed, and the modulated pulse will energize my stator winding through switch 1 and switch 4. In the second instant, because my rotor is running in the anticlockwise direction and the south pole is moving towards my Hall sensor, and now we can see that the Hall sensor is under the influence of the south pole. So in that condition, when it gets under the influence of the south pole, switch 1 and switch 4 will open, and switch 3 and switch 2 will work as a forward biasing or the short circuit, and then the circuit will get complete through switch 3 and switch 2. However, we can see that the current direction has been changed. Earlier the current direction was from left to right in this first circuit, and in the second circuit the current direction is being reversed from right to left through my motor. And the next instant, again, as the rotor moves more into the anti-clockwise direction, again my Hall sensor remained under the influence of the south pole, and the switch 3 and switch 2 will remain closed, and the current will remain in the same direction. And from here we can see that earlier, when my Hall sensor was under the influence of the north pole, the Hall sensor output was high, so this is position high, and under this condition switch 1 and switch 4 made the circuit, and the modulated pulse was given to switch 1 through switch 4, and my motor and stator winding has been energized. And this time switch, we can see that the switch 2 and switch 3 remain open, so there is nothing on the switch 2 and switch 3. Switch 1 and switch 4 are working simultaneously, making a complete. Switch 3 and switch 2 works when the Hall sensor under the influence of south pole or the output is low. So when the Hall sensor is under the influence of the south pole, the output of the sensor is low over here, and at this condition my switch 2 and switch 3 will come into action, and we have given the modulated pulse to the switch 3, and through switch 3 and switch 2 the stator winding of the motor has been energized, and therefore in this manner the switching of the single winding, or what say the single phase BLDC motor happens here. And we can see that the current is changing the direction during the high output of the Hall sensor. Switch 1 and switch 4 working, and the current direction was from left to right, and when we switch the circuit and the switch 2 and switch 3 comes into action, the current direction gets reversal, and the nothing but these peaks are that it is nothing but due to the modulated pulse. So therefore it can be seen that the BLDC motor produces some kind of a alternating current over the stator winding. Similarly, to understand the three sensor commutated BLDC motor or having three windings, two windings simultaneously has to be energized, and this is being done to increase the torque, because in the single wind commutated or single phase BLDC motor, the torque is not that much having the strength. So increase the strength of the torque, the two windings of the BLDC motor in out of three windings has to be energized simultaneously. So for this purpose, a bridge converter has been deployed, connected with the DC supply, and the my three windings of the stator, which is placed 120-degree apart with each other, are connected to this bridge converter in this manner. And to understand the working of this, three Hall sensors are being deployed on the stator A, B, and C, and all these three Hall sensors are again 120-degree apart from each other. So again, taking the same scenario, that if my Hall sensor is under the influence of north pole, it will give the high output, and if it is under the influence of the south pole, it will give the low output. So here we can see that the A Hall sensor is under the influence of the south pole, and specifically poles on road, and the B Hall sensor, again it is under the influence of my south pole, and the C is under the influence of the north pole. So therefore the output of the three Hall sensor will be 0 0 1, where A is 0, B is 0, and C is 0. So in this condition, the switch 1 and switch 4 will come into action, and the energized winding will be through this and U winding, and from here we can see that U and V winding on the stator will get energized through switch 1 and taking the that my rotor is rotating in the anti-clockwise direction. So from comparing circuit 1 to circuit 2, rotor has rotated in the anti-clockwise direction, and then here we can see that the A is coming under the influence of the north pole, is remains under the influence of the south pole, and C and again remains under the influence of the north pole. So the output of the 3-hole sensor will become 101, and in this condition switch 1 will remain into action. However, switch 4 will get open and the switch 6 will come into action, and so that the circuit will get complete through U winding, and then the W winding of my motor will be energized. Similarly, in the third circuit, as my rotor again moves in the anti-clockwise direction, I can see that the A remains under the north pole, B remains under the south pole, and the C also comes under the south pole. So the output of the ABC will become 0 0, and in this condition switch 1 will open, switch 6 remains closed, and switch 3 will come into action, and therefore the circuit will energize the winding of V and then getting the W winding and then completing the circuit. So we can see that the two windings are energized simultaneously. If we are moving again, then we can see that A remains under the N, B remains under the again comes into the influence, and C remains in this influenced, and the Hall sensor output will be 110. And in this condition, switch 3 remains into action, switch 2 will come into action, and the windings energized will be V winding, and then coming from U winding, and then making the circuit completing over here. And similarly, the last circuit completing the 360-degree rotation over, then A comes in south pole, and B comes under the influence of the north pole, and C remains under the influence of the south pole. So the output of 0 1 0, and in this condition switch 2 remains closed, but switch 5 will come into action, and the windings energized are through W, and then we have the through U winding, and then the circuit gets complete over here. So this is the last of the 360-degree rotation, where the whole sensor output will become 0 1 1, and switch 5 remain into action, and then switch 4 will come into action, and then it will complete the circuit. So taking the timing diagram for one 360-degree rotation, so we can see that we have the 3 Hall sensors output over. So in first condition, the Hall sensor output was A was low, B was low, and C was high. So it is nothing but 0 0 1, and in this condition the U winding was energized initially along with the W winding, which completed the circuit. So we have three positions over here. One is low and one is, so U winding was energized and it was remaining into the action up to the next 60-degree rotation. So this is shown for 160-degree, and this again further for 160-degree, and then we are completing the 360-degree rotation over here. So this is a complete 360-degree rotation is being shown over here, and accordingly how the UVW windings are being energized over the stator of the BLDC motor is being shown, along with the output of my Hall sensors up to. So this is for one 360 rotation of my rotor, or one electrical cycle it is being shown over. So I hope from this video we are able to understand that how BLDC motor torque speed characteristics works, and how the BLDC motor is capable to increase the torque requirement for the short period of time, and this is very much helpful specifically for the EV application, where the sudden torque can be required from the load perspective. And then how the switching of the BLDC motor happens electronically by the with the help of the Hall sensors, which is being placed over the stator of the BLDC